Well, hello there. You've made it to the video on absolute extrema. Back in the day, you probably talked about relative or local extrema, and those are the values that are either higher than all the values around it or lower than all the values around it. Well, absolute extrema, as maybe you would expect, is all about values that are higher than all the other values in a whole interval, an entire range of values. Okay, so this is a slightly different concept. Certainly, it's possible that relative extrema could also be absolute extrema, as we'll see on the next slide. So for today, the idea is that we'll go through a few examples of different types of extrema. So what is an absolute maximum? We define it as saying f of c is bigger than or equal to f of x for all x on an interval a to b, a closed interval that is, then f of c is called an absolute maximum of f on that interval. All right, so that is the case right here where I've marked 7.979, 7.917 on this particular graph. It's a value that's higher than every other value on the interval that we're given. Now, right here at x is equal to 2.029, there's a relative maximum. It just so happens the relative maximum is not the same as this particular relative maximum. This one on the right is higher, so we call it an absolute maximum. We give it a specific name there. Okay, so the picture that I have in mind when I talk about absolute maximum is a mountain range. In a mountain range, you've got lots of mountains. Some mountains are higher than others, and then in a mountain range, you might have a mountain that's higher than every other mountain. That's what an absolute maximum is. An absolute minimum is the value that's lower than all the other values on the interval. So f of c is less than or equal to f of x. So in this example, you see that we do have a relative minimum right here around x is equal to 5, but it's not actually going to be the absolute minimum because over here, as we extend to a little bit bigger than 10, we've got values for y that are smaller than that. All right, so an absolute minimum is the value that's smaller than all the other values on the interval. Collectively, of course, we call these absolute extrema. And the question is, how do we find absolute extrema on a particular interval? And they're going to only occur at relative extrema, so as we saw with the 7.979, or they could be at endpoints, as we saw with this value that's close to 10. So what we're going to do is we're going to test the y values at only those points. The extreme value theorem is going to tell us that if f is continuous on a closed interval a to b, then f has both an absolute maximum and an absolute minimum on a to b, the closed interval. So the example for that is our first picture right here. All right, if a was equal to -3 and b was equal to 2, we see that we have a highest point, that would be at x is equal to 2, and a lowest point at x is equal to -1. So every continuous function on a closed interval is going to have an absolute maximum and an absolute minimum value. That's what the extreme value theorem will tell us. If we don't have a continuous function on a closed interval, you can see in this picture right here, it's very possible that what's going on is the point where we're not continuous was where we would have our absolute maximum or minimum. So for example, you might have a hole in the graph at x is equal to -1. The function's not continuous on the closed interval a to b, and therefore the extreme value theorem doesn't apply. And so we're not assured of having an absolute max or minimum. But if we do have a continuous function on a closed interval, then we do have to have a maximum and minimum value. Where do those values occur? Well, they occur at either an endpoint or at a critical point. And this will lead to what we call the candidates test, which will be a way for us to figure out where our absolute maximum and absolute minimum values are. So let's try an example. Find the extreme values of f of x is equal to 2x cubed minus 15x squared plus 24x plus 7 on the closed interval 0 to 6. So the first step is that we're going to find the critical points of f, because you could potentially have an absolute maximum or an absolute minimum at one of your critical values. So I take the derivative and get 6x squared minus 30x plus 24. I do a little factoring, and when I set this equal to 0, I get that x is equal to 1 and x is equal to 4 are the critical points. The other sorts of points that we're going to test are our endpoints. And so we get what's called a candidates test. We have lots of candidates, just like in the presidential election, and we're going to test these candidates to see where our highest and our lowest values of f are. So we've got x equals 1 and x is equal to 4, and then our endpoints of our intervals 0 and 6. All right, and all those values we're going to put into our candidates test. It's like a debate. And we're going to say x is equal to 1. What do you think about this function? And we plug x is equal to 1 into our function, and we get 18 as our output. And then we test another critical point, something that's kind of in the middle, like a moderate. And we say x is equal to 4. Well, what do you think about this function? And f of 4 says, well, we think it's -9. And then we test our endpoints, all right? The people on the far left and on the far right of our spectrum here. When we plug in 0, we get f of x is equal to 7. And when we plug in 6, we get f of 6 is equal to 43. So our candidates test means that we try our critical points and our endpoints, and we see which ones give us the highest and lowest values. So our conclusion would be that the absolute minimum is -9. It's our lowest y value. The minimum is always a y value. We can report that it occurs at an x value, but here we would say absolute minimum is -9. You see how it's the lowest value of all of these four, which occurs at x is equal to 4. And our absolute maximum is 43, which occurs at x is equal to 6. And our lovely graph right here points that out. So our highest of all of our values on the interval 0 to 6 is 43, which occurs at x is equal to 6. And our lowest is -9, which occurs at x is equal to 4. All right, example 2, find the extreme values of f of x is equal to absolute value of f of 5 minus, f of x is equal to absolute value of 5x minus 2 on the interval -4 to 6. All right, so I kind of give you a picture here to anticipate what we're going to be looking at. But the idea is, as always, we want to find our critical points of f. So I want you to notice this is an absolute value, all right? And this absolute value is equal to the input when x is bigger than or equal to the vertex, which is at 2/5. That's when our input's equal to 0. So f of x equals 5x minus 2 when x is bigger than or equal to 2/5, and -5x minus 2 when x is less than 2/5. So that's one of the ways that we defined absolute values way back when. When we take the derivative of each of these pieces, we get the derivative is 5 when x is bigger than 2/5, so a slope of 5, and -5 when x is less than 2/5. So it doesn't look like there's any point where this derivative is equal to 0 because we get 5 and -5 here. But remember, we do get critical points whenever the derivative does not exist. And that would be at x is equal to 2/5. The reason why? Well, we get a different derivative on either side of 2/5, which is what we call a corner. Our absolute value function has a corner. So we're going to use x equals 2/5 as one of our critical points. Our two endpoints are -4 and 6. So I plug in 2/5 and I plug in -4 and 6 into my original function. As it turns out, all right, we get our absolute minimum as y equals 0, which occurs at x is equal to 2/5, and our maximum value is 28, which occurs at x is equal to 6. So as you can see from the graph, our lowest point of all the points is at x is equal to 0, or x is equal to 2/5, and our highest point is 28, which occurs at x is equal to 6. All right, find the absolute extrema of f of x is equal to x plus 2 over x minus 2 on the closed interval 0 to 4. So again, we can find the critical points by finding f prime of x, which is -4 over x minus 2 squared. So I use the quotient rule to find the derivative. And we end up with a critical point only at x is equal to 2 because that's going to make our derivative undefined. Notice there's no point that would make this whole statement equal to 0. We also want to test our endpoints at 0 and 4. So I'm making a point with this. The idea is if I were to go through and test my endpoints and plug in 0 and 4, I get -1 and I get 3. All right. Well, you might think from that, oh, okay, lowest points at y equals -1, highest point y is equal to 3. But we still have to look at what's going on with x is equal to 2. Okay, so the question is, what do we do with x is equal to 2? Well, in this case, if we plug 2 into our original function, we see that the limit as x goes to 2 from the right, like a number a little bit bigger than 2, will give us a positive infinity because we're dividing by a number that's positive, close to 0. And as we go to 2 from the left, we get negative infinity, a graph that looks like this. Well, and that tells us right away that no side goes to positive infinity, and one side goes to positive infinity, and one side goes to negative infinity, and we have no absolute max or minimum values because we're not leveling off to a single value. Well, that's an issue. And so why does that not break the extreme value theorem that we saw before, where we said we had to have an absolute max and minimum for any continuous function on a closed interval? The key word is continuous on a closed interval. This function is not continuous at 2, so therefore all bets are off. In this case, we have no absolute extrema at all because the continuity condition is not satisfied. So our last thing, how do we find absolute extrema on an infinite interval? Well, we approach this in a bit of a different way. There are no endpoints to test like in the previous problems. So we need to look at the end behavior of the function to see if that gives us any ideas about relative extrema. So our example, find the absolute extrema of f of x is equal to x to the fourth minus 8x squared on the negative infinity to infinity interval. First step, we need to find our critical point. So we set our derivative equal to 0. After a little bit of factoring, we find this happens at -2, 0, and 2. So we have 3 critical points to test. So in our candidates test, we need to make sure we include end behavior. This is a even function, so it's going to open to positive infinity on both sides. So since that limit as x goes to infinity is positive infinity, there's no absolute maximum of the function on the infinite interval. However, we can see that we get an absolute minimum, which occurs at x is equal to -2 and at 2. There's a slight little mistake here. We should have negative infinity for x is equal to 2 and x is equal to -2. And so it just so happens the minimum value is -16, which occurs at 2 different x values. That's certainly something that can happen. So in summary, absolute extrema can occur at an endpoint or at a critical point. When we attempt to find absolute extrema on an infinite interval, we need to make sure to consider end behavior. And then our extreme value theorem tells us that if we have every function continuous on a closed interval a to b, it has an absolute max and an absolute minimum on that interval a to b. Thanks for listening. We will see you on the next video.